of integrals. So let's look at the first integrals over C1. So number one. So we want to rewrite this integral of f with respect r rather. So we need to parameterize all this because really dr it's actually our differential of arc length, of arc length in terms of t, not the function, not the arc length function. Recall that that's one a little hard to get. So let's start by parameterizing this function, this first arc. So for the first arc, which is over x or along x equals y squared, we're going to have, so number one, let's write it down again, x equals y squared. And well, in this case, notice we have a function of y, not a function of x. This time is x, the one that depends on y. And recall that one of the easiest ways to parameterize a curve is to let the independent variable to be the t. In this case, well, the independent variable is y, so the y component, that's going to be t. So if y equals to t, substitute that t into x equals to y squared, that becomes x equals to t squared. Are you guys following me here? All right. So that's our parametric equation of this x equals y squared. Well, later we will look at this picture of what it is. And again, one of the advantages of just giving the independent variable, the variable t, is that in this case we know for sure that this will vary between, or rather t will vary between 0 and 1. Right? I mean, of course, you can parameterize that curve x equals y squared into something else, into another function. You could even parameterize it using exponential functions, trigonometric functions, you name it. However, let's keep it easy, just letting t our independent variable. And that's because we also get the limits 0 to 1. And you know how easy it is to integrate between 0 and 1, right? So, well, what do we need in this case? So we need the derivative r prime which is in this case the derivative, that's 2t and 1. And well, what are we going to need in this case? So number one, let's go back to the integral over c1. That's the integral from 0 to 1. And in this case, what do we have? We have a vector valued function, and in this case the x component, the y component, that's going to be x y squared, which in this case, what's x in this case? Isn't it x equals to t squared times y squared? I think I'm going to need more space here. Times y squared, that is y, which is that quantity squared, but y in this case is t, all right? Comma, let's go to the y component. So that's x squared, that's some quantity squared, and that's a t squared, times y, which in this case is simply t. So that's our f. Our f evaluated in terms of t, right? Let's write down so we can do the dot product between the differential vector that came from the derivative, because that's the same as saying f of t and r prime dotted with r prime of t dt. All right, this dr becomes r prime dt. And well, so that's going to be simply 2t comma 1. Okay, so this will be equal to the integral from 0 to 1. Let's simplify this. So that's t squared times t to the second. Isn't that t to the fourth? And that is, be careful with the second component. So power of another power, multiply the powers. That's t to the fourth power times this t. That's a t to the fifth power. All right, and that's dot product with 2t comma 1. And recall that the dot product just multiply the components. So t to the 4th times 2t, that's the integral up to t to the 5th power. And plus t to the 5th times 1, that's simply t to the 5th. dt from 0 to 1, combined like terms, that's the integral of 3t to the fifth dt from 0 to 1. And well, this integral, which is just general power rule, how about that's just going to give us a 1/2. All right. So that's the first integral, and that's over the arc x equals to y squared. Let's see what happens over the second arc, which in this case the second arc is y equals x cubed. Now be careful with the second arc, because in the first arc the independent variable was the y, because we had a function x depending on y, so the independent variable is y. That's where we assign the t to the independent variable. This time the independent variable is x. So when we parameterize that function, so when we parameterize y equals x cubed, well, in this case, again, the independent variable is x. R of t is the vector valued function t comma t cubed. Because plug in t over x, where whatever you see the x, well, that's t cubed. And we'll need to make sure that this is going to vary, or the t is going to vary between 0 and 1. That's always a freebie one. Again, I'm going to repeat this many times, so it's, it's always there. Every time we parameterize by assigning our independent variable the variable t, that for sure is going to permit us have t value vary between 0 and 1. Find the derivative. That's 1 comma 3t squared. And well, I guess we're ready to evaluate the integral. All right, now be careful when substituting. So that's the integral from 0 to 1. And I think I'd better write the vector valued function again. So let me write it at the top. Well, you guys have it on the paper. I don't have it here. So that's xy squared comma x squared y. Okay, so x, which is t, times quantity squared, which is y squared, where y is t to the third power and to the second power, comma x squared, which is quantity squared, where the quantity is t, comma y, which is t, oh, not comma, actually it's times t cubed. And well, what about the derivative? Okay, so just write down the derivative. That's 1 comma 3t squared. All right, and then dt. The rest is simplifying the vector valued function, the first factor. So that's the integral from 0 to 1. That's, well, careful here. Power of another power, we multiply the powers. That's t to the 6th times t. That's going to be t to the 7th. And over here, t squared times t to the 5th, times t cubed, that's t to the 5th. And everything else remains the same. So let's do the dot product and obtain a scalar function here. 0 to 1. Oh, no more brackets. So t to the 7 times 1, that's t to the 7. And t to the 5th times 3t squared, that's 3t to the 7 with dt, which is the integral from 0 to 1 of 4 t to the 7th power dt. And after integrating this, that's going to give us a 1/2. Interesting result, isn't it? We're getting exactly the same result okay, so notice, let's go back to the definitions of our arcs. So in this case, this is what's going on. We're going from the point 0, 0 to the point 1, 1 over c1, but actually c1, since it's a function of y, x equals y squared, that means y equals the square root of x. Well, technically plus or minus, but because we're going through the point 0, 0, and 1, 1, I'm just going to take the positive counterpart. And in this case, let me call this C1, all right, which is x equals y squared. And on the other hand, we're going to go to the same point from 0, 0 to 1, 1, but in this case, by means of the cubic function in this case, that is C2. Two totally different functions, but we're still getting the same. I mean, why would that be? So I guess if we make up another path, C3, I claim that we should get the same result. But why is that result? Why is that happening? So there's another part for this question, for this preliminary work, that is to determine whether F is a conservative vector field. Well, that's something we discussed last time. It's going to work really good for review for today. Well, number one, what do we have? So we have the vector field big F of xy. That's xy squared comma x squared y. And well, in this case, we need to identify our little f and our little g, where little f is xy squared and little g x squared y. So in order to determine whether that vector field is conservative, we need to perform a test. We need to determine whether f, the partial derivative of f with respect to y, is equal to the partial derivative of g with respect to x. Let's see if that is the case. So what's the derivative of the f component with respect to y? Isn't that 2x y? And the derivative of the y component with respect to x, take the derivative of x squared, that's 2x. Oh, 2xy. So because we got both partial derivatives the same, what do we conclude about it? It's conservative, all right? So it's conservative, and if so, well, in this case, they're asking us to find the potential function. That is the phi of x, y. Well, in this case, it's a two-dimensional case whose gradient, nabla of phi, is that vector field that we have in terms of x, y. So let's go ahead and do that. Recall that we need to do a couple of partial integrations and then reconcile everything into one single piece. So number one, phi of xy is going to be the integral of f with respect to x, which in this case is the integral of xy squared dx, which is x squared y squared over 2, plus potentially some constant of y. In this case, the other variable, the one that we are not integrating with respect to. All right, let's do the second partial integration. Phi of x, y, equals the integral of g dy equals to the integral of x squared y dy, which in this case it happens to be the same, x squared y squared over 2 plus, in this case, c of x. Yes?
Isn't f equal to xy? I think that first one.
Which one?
Never mind.
Well, no, that's fine. Which one is it?
Never mind.
Oh, okay, don't worry. No, that's fine. That's fine. So, okay, let's have a look at both partial integrals. In this case, well, we got the same on both partial integrations. We didn't get anything different on any case, so it looks like the potential function phi of x y equals to x squared y squared over 2. And again, this is what my MATLAB is asking you to type, only that function. But again, recall that last time we discussed how, in a way, I kind of disagree with this, because when we're integrating, we will be expecting some potential constant, like +5, +3, and I mean, it could be there, all right? But don't write the plus k on the blank spaces on my MATLAB, all right? Well, what is this all about? Why are we doing this exercise, this preliminary work? I mean, that we are essentially finding the line integral over the same vector field, however, along two different paths, and we are obtaining the exact same result. And then as another piece of information, it turns out that the vector field over which we are integrating to happens to be a conservative vector field. There has to be a connection between those two ideas. And that connection, that idea, is formalized in the next page. And this is actually the fundamental theorem of line integrals that says that f be a continuous vector field of an open connected region R in R2 or R3, depending whether we're working on the 2D plane or the 3D space. If there exists a potential function phi such that its nominal phi equals the vector field, in other words, if we know that f is conservative, then all we have to do is find that conservative vector or that potential function and evaluate it at the order pairs, at the upper order pair and the lower order pair, and we don't have to parameterize anything anymore. But this is only possible as long as you know for sure that your vector field is conservative. Otherwise, we would have to parameterize and do it the long way. Even potentially make it piecewise smooth, like the one that we did last time where we had to parameterize actually 3 pieces, you know? Well, now this is one of the biggest results ever here. Well, so as an example to illustrate this, use the fundamental theorem of line integrals to evaluate the integral from our previous page. All right, so what are we supposed to do here? Well, so just use our big F, which in this case is xy squared, x squared y, and well, we got that this is a conservative vector field, and our phi of x, our phi of xy, which is our potential function, is x squared y squared over 2. And well, in this case, the point A was the point 0, 0, and the point B is the point 1, 1. Well, what is this fundamental theorem of line integrals? Okay, so let me go back to the previous example for a couple seconds. So this means, in a nutshell, the fundamental theorem of line integrals tells us that if we have a conservative vector field, it doesn't matter the path you follow to go from point A to point B. The value of the integral is going to be the same. In other words, the work done by this vector field into moving the particle from point A to point B is independent of the path. I could have gone, I don't know, let me make something crazy here. So this is point A, this is point B. I could have gone like this, you know. If we can parameterize this crazy line, well, I got to be, it's going to be the same work. It's going to be a 1/2. The result of the integral is going to be 1/2. If I go piecewise along this horizontal line and then vertical line, the value of the integral, it's still going to be 1/2, because having a conservative vector field ensures that the value is exactly the same, regardless of the path that you follow. All right, so using that fundamental theorem of line integrals, so we may now evaluate the integral of f dr over c, that is simply the potential function evaluated at the point A, actually at the point B first, it's minus the potential function evaluated at the point A. Yes, I got it right here. And well, this is in this case the potential function at 1, 1 minus the potential function evaluated at 0, 0. And well, we have a potential function that we just found, didn't we? Well, So that potential function happens to be 1 squared times 1 squared over 2, because x and y are both 1 on the endpoint. The second point, or the final point minus initial point, which is 0 squared times 0 squared over 2. And well, 1 squared is 1 times itself is 1 divided by 2. That's 1/2. Minus 0, isn't it the same result? So, well, as long as you have a conservative vector field, forget about parameterizing anything in f of b minus f of a. I mean, it's like the fundamental theorem of calculus, evaluate at the upper limit minus the lower limit, but in this case is upper point or final point minus initial point. That's it. Common pitfalls. A common pitfall is not to find the potential function and do the integration over f. No, f is the gradient of phi. Just be careful with that one. So let's get more practice on this. So let's now use the fundamental theorem of line integrals. Consider the line integral over c of f dr, where c is a piecewise smooth curve from 1, 0, 0 to 3, 1, 4, and the given vector field is, well, that madness there. Now, well, I mean, even parameterizing this line segment, I mean, we know how to parameterize that segment, and it shouldn't be a big deal. But in this case, well, number one, let's determine whether the fundamental theorem of integrals apply to this situation, so we can evaluate that integral using deduction. And if so, well, so what do we need to do? Number one, we need to take 6 partial derivatives and make sure that we have the same on certain cases. That is to show that the vector field is conservative. So on the one hand, let's identify f, which is 2xy, g, which is x squared plus z, and h, which is y plus 4. So on the one hand, we need to make sure, or we need to determine whether the partial of f with respect y equals to the partial of g with respect x. Let's see if it is the case. So the partial of f with respect y, that's 2x. And the partial of g with respect x, the derivative of x squared plus 2, that's 2x. Well, so far so good. So the first condition is satisfied. However, we need to make sure about 3 conditions, not just 2 conditions, not just 1 condition. The second condition, well, I'm going to call this letter A. The B condition is that the partial derivative of f with respect to z equals to the partial derivative of h with respect to x. Let's see if that is true. So the partial derivative of f with respect to z, well, we don't have anything with respect to z, so everything is constant. The derivative is 0. What about the derivative of h with respect to x? Also 0. It's only y plus 4. All right, so second condition is satisfied. The third condition, which I will label as a letter C. All right, so for letter C, this is to make sure that the partial derivative of g with respect z equals to the partial derivative of h with respect to y. So g with respect z, that's 1, and h with respect to y is also 1, so the 3 conditions are satisfied. If at least one of these 2 conditions fails to be true, well, then the vector field is not conservative. We may not use the fundamental theorem of line integrals, so we will have to go the brute force way by parameterizing the whatever path we were working at. All right. Well, now that we found out that that the vector field is indeed conservative, let's do partial integration to find out what that potential function is. So, and in this case, this is a three-dimensional case. Well, it's going to take a good minute to go. Nothing crazy anyway. Oops. Phi of x, y, z, that's the integral of f dx, all right? The first component with respect x, and then the second component with respect y, and then the third component with respect z. So, that's the integral of 2xy dx, which is x squared y, plus, in this case, some c that depends on what? Y and z, right? Because we integrated with respect x, so that's going to depend on y and z potentially. And we may get something that depends on y and z in the other two partial integrations. We'll see. Let's find out. X, y, z, the potential function, that's the integral of g dy. And in this case, well, so that's the integral of x squared plus z with respect to y. That's simply x squared y plus yz or zy. Do you see this yz is indeed some function of y and z that we would have expected in the first integration? So I think we can already start thinking of reconciling everything to form this potential function. And in this case, well, that's some function c of x and z. Let's do the third partial integration. That's phi of x, y, z. And that's the integral of h with respect to z. Well, so that's just the integral of y plus 4 with respect to z. And in this case, that's y z plus 4 z plus c of x, y. Okay, now let's observe all the results from the partial integration and reconcile into a single one. So, f of x, y, z will be, okay, so in the first integral we got some x squared y. Okay, do you see another x squared y? Well, we see another x squared y in our second, but we need to list it only once. We don't combine it, we don't add them together. Okay, do we see anything else? Well, that yz, right, on the second partial integration, and the third one, that's just write it once. Do you see anything else, anything different? The 4z, right? And of course, I mean, plus some k, but I mean, in this case, it's fine not to write that k, because ultimately we're going to use the fundamental theorem of line integrals. Those k's would cancel, whether it's a 5, a 1, a 7, so in this situation, it's fine. So, this means that our integral of f dr, and again without parameterizing anything, just using the fundamental theorem, that's going to be phi of the endpoint, the final point, minus phi evaluated at the initial point, which is 1, 0, 0. That is, this function, this madness here, x squared y plus y z plus 4z, evaluated from 1, 0, 0 to 3, 1, 4. It's the same fundamental theorem, but in this case with 3 variables, if you will. All right? And let's substitute everything. That's going to be, okay, careful, because we have x's and y's and z's all over the place. Be careful with what did you plug in and where. So x squared, that is 3 squared, y, which is 1, and plus y, which is 1, times z, which is 4, and plus 4 times the letter c, which is 4. So that's the upper limit minus lower limit, okay, x, which is 1, that's 1 squared, times 0, plus y, which is 0 times z, which is also 0, plus 4 times z, which is 0. So everything for the lower limit is 0. I mean, I could have said that in the beginning, but the reason why I'm plugging in everything just so you can see how it works in the case in which you don't get all zeros every single time, all right? So that whole thing goes to 0, so that's 9 plus 4 plus 16, which adds up to 29, all right? So that's one example from scratch about applying the fundamental theorem of line integrals. So let's go ahead and do another example. So let's see. Consider the vector field f of xy equals 3 plus 2xy in the direction of I plus x squared minus 3y squared in the direction of j. Find a function f such that big F equals nabla f. In other words, they're asking us to find the potential function. And then evaluate the integral f dr, where c is the curve given by this vector valued function over that given integral. All right, well, let's see. So number one, let's find the potential function. So in this case, I'm a little confused with the notation because we were supposed to use, phi, right? Well, let's just call it f in this case. So let's integrate. Oh, by the way, let me make a comment about fundamental theorem of line integrals and conservative vector fields for if in case that you use other resources such as other textbooks or the internet. In this case, well, we call these coefficients of I, J, K as F, G, and H. However, in other textbooks and in the internet, YouTube, or whatever you look at, they also call it M, P, and Q. All right, just so when you see it in different resources, well, they just change the letter, but it's ultimately the same. I mean, all right, just labeling things, So let's call this time big M and big N. Capitals. Capital M and capital N. So we're going to find let's evaluate, let's get our f of x, y, our phi. So let's do first of all the integral of m dx, which in this case is the integral of 3 plus 2xy with respect x. That's going to be 3x plus x squared y plus some c of y. Well, in this case, we're just working with two variables, not three. And the second integral, which is the integral of n dy, that's the integral of x squared minus 3y squared with respect y. So that's x squared y minus 3y cubed over 3, which actually just reduces to just y cubed, plus some c of x. All right? So let's put everything together to find that potential function. This time, I'm going to call it f, not phi. So f of xy. And well, what do we have? We have a 3x right here. We don't have another 3x. Well, just bring the 3x. X squared y. So that x squared y, it's also on the second partial integration. That's plus x squared y. And this negative y cubed, which is, the potential function of y that we would have obtained in the first integration, but it actually shows in the second integration, so that's a negative y cubed. And well, of course, plus some potential k, right? And that's why I just put it in parentheses because, just to make sure that you don't put it in, that you don't type it on MyMATLAB when inputting your results. All right, so now that we have a function f of xy, which is the potential function, let's evaluate it over the curve given by this parametric function. That is, let's see. So the thing here is that this time we are not given, we are given this as a parametric function, that is a vector valued function. Well, recall that every time that we list a vector, like the vector 3, 1, that's actually the terminal point between two segments, in standard form, between the origin 0, 0 and that point as the terminal point. So in this case, we are going to use, because we are not given the initial point and the final point, we're given a vector valued function, so we're going to plug in these values of 0 and pi to the given vector valued function to find the vectors related, and those vectors we are going to take them as points. You'll see what we're going to do here. So r of 0 equals, number 1, e to the 0 sine 0, comma, e to the 0 cosine 0. And in this case, what's the vector when t equals 0? So, or the position, well, in this case is e to the 0, which is 1, cosine of 0, which is 0, that's actually a 0, e to the 0, which is 1, cosine 0, which is 1, 1 times 1, that's 1. All right? But again, like I mentioned before, we can turn this vector into an order pair, a point, because this is the terminal point where the vector is going through when t equals to 0. So we turn these angular brackets into parentheses for that reason. All right? And r evaluated at pi, that's going to be e to the pi sine pi e to the pi cosine pi, which in this case, well, sine pi, which is 0, and so again this is going to be a 0, and cosine pi, which is -1 times e to the pi. Well, e to the pi, let's just leave it as e to the pi, so that's e to the pi, and actually negative, right? And turn that vector, turn that vector into an order pair for the same reason as we discussed before. Okay, so that turns into the point 0, negative e to the pi. Oops. All right, so now that we have a potential function, and now that we know the order pairs at which the particle is going to and from, well, let's go back to the line integral of c f dr. And this is, in this case, simply f of a minus, again, f of b minus f of a, which in our particular case is f evaluated at the point 0, negative e to the pi minus f evaluated at the point 0, 1. All right? And let's just use our potential function in this case to do such evaluation in this case. So that's going to be 3x plus x squared y minus y cubed evaluated between 0, 1 and 0, negative e to the pi. And let's just use upper minus lower on the potential function here. So that's a 3. Okay, for the upper limit, that's 3 times x, which is 0, plus x squared, which is 0 squared, y, which is negative e to the pi. Well, that's going to get zeroed out anyway, minus e to the negative e to the pi quantity cubed. And be careful with this last quantity. And then minus the initial point, which in this case, that's 3 times x, which is 0, minus, or plus rather, 0 squared y, which is 1, minus y cubed, which is 1 cubed. And let's simplify this result. Well, a lot of terms, a bunch of terms actually, go to 0, get zeroed out. That's the first term, that second term, this term, and that term. So we will be left with only 2 terms in here, but be careful because number 1, this negative quantity is being cubed. When we're cubing, that is, we're raising to an odd power, the result remains negative. Agree with that? However, we have another negative sign outside. That's going to turn it into positive. So that's e to the pi cubed, and then minus negative 1, which is plus 1. Do we all agree with this? Yeah, that's e to the 3 pi, right? Power of another power, the powers multiply. Careful with those laws of exponents, you know? And well, that was another example of using the fundamental theorem of line integrals. And